UFO. Okay, so thanks a lot for inviting me. I have the main topic of this talk is about our superfluid experiments, and these experiments are led by Laura DiLorenzo. Who can raise your hand? Yeah, so Laura is the grad student who's willing to try to do this experiment, and you know, the description of where we're at right now probably would take probably about 30 minutes or something. So what I thought I would do is give you a tour of where quantum effects and mechanical systems are at, just to kind of let you know what's possible in small mechanical systems. And then for the last half of the talk, I'll tell you about why we thought about superfluids as something interesting, and then what we're doing there. So that's kind of the outline of what I was thinking. So there you go. So this is the superfluid stuff, and then I'll give you just a tour of what's possible. So my interest in all this goes back to when I was an undergrad or even in grad school, and hearing about gravitational wave detection, and then eventually finding this book when I was a grad student around 1992. And you know, the book is just the experiments that we pursued in my lab often are taken directly out of the various chapters in this book. And right now the field is up to about chapter 10, where we're doing back-action debating measurements, and that's where we're at. So Caltech has a big influence on what we're thinking. What got me solidly into this and thinking that small mechanical devices would be interesting for as really intriguing experiments was essentially the idea that I'm going to describe here. And the idea is how to think about how you would actually produce a superposition state of a mechanical structure. And for those who have heard me talk about this before, I apologize for being redundant, but this is kind of the core idea of why I think this is an interesting area of physics. So I thought I would just mention it again. And the basic idea is that find a quantum two-level system. And you know, imagine here you have like a spin, it could be a qubit, it could be whatever you like, something that actually has two possible levels, maybe more, but at least two, and that actually follows Schrodinger dynamics and can actually support a superposition state, right? It actually will have a superposition state. And engineer a force with some mechanical structure that depends on whether the state is up or down. So imagine, you know, Dan Rugar's MRFM, magnetic force microscope, with a single spin on a substrate and a cantilever above it, say. That's a physical realization that's real. Okay, so the idea is that if you put the spin into the up state, it pushes the mechanics over to the left, and if you put the spin into the down state, it pushes it to the right, and the state of the system, mechanics plus spin, looks something like this. And then if you go into a superposition state for the spin, the force now has to act on both up and down, and mechanics, quantum mechanically, should evolve into both left and right. And in the end, if the force is big enough, you can end up with an entangled state where this is non-separable here, where the distance between the right mechanical state and the left mechanical state, if it's greater than the uncertainty principle for the mechanical device, then this is an entanglement here. And so this is kind of an idea, okay, it's not a particularly new idea. There's optical realizations people had for a long time. But when I started thinking about this stuff in 2000, around there, what was happening in the field was various artificial two-level systems, qubits. And when you think about how you could engineer coupling to some superconducting circuit, you found out that the forces are much bigger than electron spins and nuclear spins, and that one could actually get displacements that are larger than the uncertainty principle for a mechanical structure. So that was that's the engineering piece of this, that the coupling can be strong enough. And so best qubits now, you can get lifetimes of 100 microseconds and coherence times over 10 microseconds. So you can really interact these systems with some amount of time to a mechanical structure. The next realization that made this interesting to pursue, to kind of head down this road, was to think about the decoherence times. So from this classic paper from Zurich, Habib, and Paz, they calculate the maximum decoherence rate for a superposition of two coherent states. So you pull apart a mechanical structure, a SIP harmonic oscillator, by a few line widths, a few zero-point level, uncertainty principle widths here. And this is what you compute for the decoherence time. And in the end, it only depends on the temperature, the Q, and then the separation of how big the superposition is, normalized by the uncertainty principle. if you plot this function for Q of 50,000, and you take the uncertainty principle as maybe 3 times the standard quantum limit, then what you find out is that the coherence time should be microseconds. And the Qs here, I've assumed are actually low. You can get, Qs now hundreds of thousands. Recently, people have measured Q, I was just mentioning it, 30 million, 40 million in silicon nitride membranes at room temperature. So you can exceed this estimate that I have here by a few orders of magnitude. And so that's a lifetime of microseconds for a superposition state of a real mechanical structure. So seeing this formula and seeing this made this like, okay, this isn't crazy. This is within what's possible. It might be challenging and hard, but it's within what's physically possible. So ultimately, we headed down this road together with Jun Ho and Matt LaHaye and Mike Rukas. Here at Caltech, we had actually made, together with Pierre Ectronog at JPL, made a device that had a qubit and a mechanical structure. And in this experiment that reported in Nature, and it was like 2009, if I remember right, yeah, 2009, what we actually measured was measuring the mechanical frequency would determine the state of the qubit through a cavity QED like Hamiltonian. So this is the mechanical resonator, this is the qubit, and then there's an interaction term here which depends on the position of the resonator. And in this kind of very strongly detuned limit, it acts like it's just a dispersive interaction where the state of the qubit just pulls the frequency of the mechanical structure. And so by looking at the frequency shifts of the mechanics variant versus the qubit biasing points, either charge or flux, you could actually determine the state of the qubit by measuring the frequency of the mechanics. It's like doing cavity QED physics, looking at the frequency of a cavity and determining the state of an atom. Okay.
Keith, can I just ask? So the qubit is sigma z?
Yeah, that's right.
And I also see a sigma x.
Yeah, that's right. So, depending on the exact bias point, you can either have the eigenstates along sigma x or sigma z. So, if you're in the charge eigenbasis, then you're in sigma z, and then when you're at the degeneracy point, this term is 0 and you're coupled to sigma x. This is the Josephson part.
And this is desirable? You engineered it to be like this?
Yeah, it's kind of what nature gives you when you just put an electrostatic voltage next to a qubit like this.
So you can't avoid it?
Can't avoid it, yeah.
But it doesn't cause like more decoherence or more difficulty in measuring it?
At this level that we were at here, we were just looking for frequency shifts. So the coherence aspect we weren't probing. And it turned out that the superconducting qubit we were using had very low coherence. So we weren't able to make superposition states of the mechanics or superposition states of the qubit because the lifetimes were too short. So we just put our toe into this area of putting a qubit next to mechanics. Now the real tour de force in this kind of experiment was at Santa Barbara 3 years ago, with Andrew Cleland's work, where he had put a phase qubit, which was much better behaved, coupled strongly to a mechanical resonator. And it wasn't this kind of dispersive cavity QED interaction, it was actually, they were degenerate. The frequency of the mechanics equaled the frequency of the two-level system, and they just exchanged quanta. So you could put the qubit into the excited state, and it would just Rabi oscillate. It would then send one phonon over to the mechanics, and the mechanics then would exchange it back with the qubit. You could just play ping pong back and forth with 1 h bar omega a couple cycles. And that, historically, I will believe when we look back at this field 10, 15 years from now, we'll identify that experiment as the real entrance into the quantum regime for mechanical things. So this week, luckily we published this before that experiment, otherwise there's no chance this would have made it into a good journal, but this was us just getting started in this area. So anyway, so our group had done a bunch of stuff over the years in this area. This is just trying to give you a little tour of what we were thinking. When we first got started making mechanical resonators, we could measure it down close to the SQL with these kind of devices and we just passively cooled our fridge down to 25 quanta. And then eventually we learned more about the back action physics, and we could actually see the mechanical resonator kicked up by the shot noise of the detector. And so this is very similar to what Cindy Regal's reported in Science this week with optical detection, where they have a cavity and then a silicon nitride membrane. And in that circuit they drive photons through the device and see the mechanical device heat up, the mode heat up. In this experiment we reported back in 2006, it was sending electrons through a detector and seeing the mode heat up due to the shot noise of the impact of those particles we were using for measurement. So anyway, then we moved on to back action evasion, and I'll talk a little bit about that. And then the rage in the field over the last few years has been about cooling, preparing the ground state. And Junho has recently prepared n equals 1 down in the lab now. So we have a device that's in the ground state about half the time. Okay, so we can skip over that. Okay, so the basic physics of this device, of what I'm going to tell you about some of the history in the group experiments, and also the superfluid device, is about parametric transducers, something that the LIGO community knows in spades, and this optomechanics community either doesn't read the papers or ignores the papers, or the 30 citation limit on Nature causes people to drop those papers. But a lot of what is written currently in the most prestigious journals is very similar to what was known in the gravitational wave literature from more than 20 years ago. But the physics is really simple. It's an LC resonator, and then some finite friction, and then you can pump it anywhere you like. And the capacitor, let's say in this case, is modulated by, it's attached to some simple harmonic oscillator. And in this kind of circuit, here's the electrical resonator. Here's where I place the pump. And then this is up in our case, is around 5 gigahertz. And then our mechanical device is down here at 5 megahertz. So harmonic motion of the mechanical device will cause sidebands to appear on the pump. And it's just due to the phase modulation of, from pulling this cavity back and forth at some frequency. So you'll get one sideband if you tune everything right in the cavity, or in this LC resonator, and then one sideband off resonant here. And due to just the circuit dynamics, just from the fact that you're on resonance, this sideband appears bigger than that sideband. And that's important if you want to cool or heat or do whatever. When you go through the classical physics of all this, what you find out is that the charge that's on this plate here is modulated both by the pump voltage and its mechanical motion. So you end up with something with bilinear terms here. This is pretty obvious. And this is where you get the two frequency up conversion and down conversion. Okay, but like I said, this is old stuff. Mark Bacco had understood so much of this, and also Berginsky and those guys had gone through a lot of this.
You just pull the screen down a little bit.
Oh, sorry. There you go. I think we're just missing 2 pixels at the bottom. Okay, so those up and down converted photons here, these two sidebands, quantum mechanically they're interesting in that if I send in a pup photon and I get out something bigger, I had to absorb a mechanical quanta. So this sideband here, where I have a bigger photon come out than what I applied, actually sucks up mechanical quanta. The sideband on the lower side emits one mechanical quanta, and the photon appears at a lower frequency. So it's this one here. Once you're in the ground state of the mechanics, you can't suck up any more mechanical quanta. So this sideband actually goes to 0 if the mechanical device is in the ground state. This sideband here, you can always put in a mechanical quanta into the mechanical device. So this one has a spontaneous emission part, which is the +1. This is really interesting because if you can get to a cold enough state and you can measure the difference between these two sidebands, you can then determine the uncertainty principle in this circuit. And this is what Oscar Painter's group has just recently achieved in the last year or so, where they actually see clearly the difference between n and n+1. Okay? So it's the first time that in a mechanical circuit that's just been engineered, you can identify the uncertainty principle part. Okay? We are on the track of this as well. Junho, Ari, and Chan, you and I are also looking at this in microwave circuits. We see an imbalance between the up and down conversion, but right now it's a little too big to be understood by quantum mechanics. It's about 10%, 20% too big. We're trying to sort out what the details of our circuit are that are giving us some extra back action forces. But anyway, we do see an imbalance as well. But Oscar's group had just got it just right. So these experiments that I described go on the bottom of a dilution fridge. We have 2 of these fridges down at the basement of Sloan. Are the base temperatures of the fridge. One of them is 5.5 millikelvin. The other one was measured to be about 7 millikelvin. So that's where all the devices go in. The structures that we're working with right now that Junho is working, and Ari and Chan Yu are working with, look like this. Here's an SEM photo. If you took a cross section through this, what you find is a silicon nitride membrane that has some aluminum on it, and then there's a top gate here that's a fixed gate. It'll have its own vibrational modes, but the mode we're interested in is the one down here. It should have higher Q and strongly coupled. So what you're seeing here is the top gate, And then these holes are allowing you to see the metallized silicon nitride membrane here. And then it goes to an inductor. So this is the LC. If you back out, you can see this is the feed line into the circuit. We pump it at 5 gigahertz. This is all superconducting aluminum in this case. Then we feed it into where there's the mechanical device and then an inductor. This is a different generation device where we had a separate capacitor and then an inductor. We moved the capacitor, the mechanical element, into the center here for various reasons. But anyway, the point is this is what kind of the big layout looks like on these kind of circuits. And then if you look at this, so I showed you a picture zooming in here. If you zoom out a little bit, here's the inductor. There's a wire that has to be fed in and not touch, has to cross over. We feed microwaves in through this capacitor. We detect the microwaves coming out through that capacitor. So that's more or less the same there.
Do the holes play a function, or they just?
They're there to help the release of the device. So we're trying to get a very narrow gap here. We'd like it under 100 nanometers. Our gaps are typically in 200, 250 nanometers. And Junho and Ari and Chenyu, they use a polymer that they need to dissolve away that sets the gap.
What about the holes in the outer substrate? Zooming out.
Oh yeah, those are to trap flux. Those are essentially to trap flux in the earth scale. We put all kinds of magnetic shielding around our device to try to cool it in a flux-free environment. But okay, so you can take that device, you put it into a microwave package, you put it on the end of the dilution refrigerator. You bring in a feed line that's carefully filtered from room temperature black body radiation. You then go into an ultra-sensitive hemp amplifier, and if you pump it on the red sideband, you'll start up-converting quanta into the cavity, and you can start to see these mechanical. These are the peaks that are those mechanical. The sideband that's from up-conversion. That's what's shown here. And if you take the area of these peaks and plot them versus the temperature of the fridge, you can just see the equipartition relationship. And you can just, it's a reasonable precision, and it plots down to the origin. And the lowest temperature points here correspond to something like 10 millikelvin, 8.5 millikelvin for this peak here. So it's amazing. You can really take this device and put it on the end of a fridge and it just thermalizes with the fridge. And for those, we've been involved in experiments like this for a long time. We have other designs which do not do this, just so you know. We have designs that are crappy, where you come in and you start cooling off, and then as the Q improves of the mechanics, you see the power, the temperature of that mode diverge. And we've never figured out what that problem was, where it came from. This kind of device does not show that kind of behavior.
This is just the upper sideband?
This is just the upper sideband, yeah.
So is that showing that the frequency of the mechanical oscillator is changing as
you
cool it?
That's right. And that follows a log dependence, which is classic two-level system physics. You expect a correction to the speed of sound. If you take a piece of glass, you put it on a dilution or on a refrigerator, measure the speed of sound in the glass, it shows a logarithmic dependence in the speed of sound. These devices show that same kind of log dependence. So if you take that red power, red power, I don't even know what that means, but you take the red power and you start turning it up. So here's the pump photons. You start turning up and so you increase the rate at which you're scattering those up-converted photons. Eventually you start broaden the mechanical device, the mechanical line. And here's the line width of the mechanical structure as you increase the power. So you can take it from 100 hertz up to 20 kilohertz in this particular device. Okay. So as you broaden it, you're adding damping. You're scattering out the mechanical quanta faster than they're coming into from the thermal bath, and you should start to cool the device. And so indeed it cools. So here's the occupation number. This is the, sorry, I don't have the label here. This is the mechanical occupation number. How many quanta are in the mechanical device? So we start off with 20, 30, 40 quanta, and then we turn up our microwave power. We start scattering faster and faster, and eventually it cools. The device cools and cools. The occupation hits somewhere near 1, and then eventually it starts getting worse. And what's getting worse is that the cavity itself, the actual microwave circuit, starts to get occupied with 1/10 of a quanta, 1/4 of a quanta, just in broadband noise, but it's just a tiny amount of power. And you can show using the detailed balance equations that you can never cool your mechanical mode below the occupation factor of your high frequency mode. So those, eventually they just come into thermal equilibrium now. Mechanical quanta equal the cavity quanta. So you have to have a cold cavity in the ground state if you want the mechanics to hit the ground state. But the point here is that as you pump the cavity harder, the cavity starts to become occupied. Junho and I think this is a result of the fact that the cavity has some frequency noise, some jitter. And this is well known in the superconducting detector world, where they make M-kids, they can measure the frequency, and they see pure frequency noise of the M-kids. We think this is the same physics that's limiting us here. Okay. But this is ubiquitous. If you look at all the plots of people doing this kind of work, so our group, John Toffel and the guys in Jilla, they get down to about 0.3 before this effect happens. There's a group in Finland that got down to 2, and then this effect happens. And it's all a result of the occupation of the cavity. So until somebody figures out how to get rid of the two-level system noise in this kind of structure, we're going to really be limited by how far we can cool. So you might want to say, like, well, do you really want to cool further? Is it useful? Well, you really do want to cool to 10 to minus 1, 10 to minus 2 if you're going to prepare some state and then go to some other state. So you'd like to know where you are and then prepare, then try to prepare some other state. You don't want to start with a 50-50 mix of ground state plus something else and then try to go somewhere else. You want to start with pure ground state and then move from there. Okay, so just to kind of continue the tour in this area of what's been possible, getting down to, you can get close to the SQL in your measurements, you can get close to the ground state now, mechanical structures, microwave structures. You can start to see some quantum mechanics in the sideband imbalance. The next thing to try to see, which is chapter 10 of Brzezinski, is two-tone measurement and try to avoid the back action. Okay? So the quantum back action in measurement comes as a result of this loop here, where I measure position, but the fact that x and p don't commute means that I'll always perturb the momentum. And then the Hamiltonian dynamics connects a perturbation momentum back to a position later. Right? So it's just this loop. And so as I push harder and harder on x, I get more and more changes in p, and eventually that affects the next x even worse. And there's a minimum that you can get to. This is the standard quantum limit. Okay. So if you can get rid of this loop, then you can avoid the SQL. This is all well-known physics from Brzezinski in 1975. The folks here at Caltech, in 78. Yeah, so this is old stuff, and then there was a re-look at this by Osh Clerk and his collaborators in 2008, where they did the full quantum treatment, input-output theory of the device, and wrote down all the quantum limits for this. So what I'm talking about here is actually a two-tone measurement, where you're measuring the two quadratures rather than the full position. So you can always dissolve a position into x1 cosine omega t and x2 sine omega t. And so if you can figure out a way just to measure x1 and not see x2, then you can avoid all this back action. So x1, it turns out that it does not commute with x2. That's obvious because, at time equals 0, the position of the oscillator is x1. But at time equals 0, the momentum of the oscillator is x2. So there's no way that x1 and x2 can commute at the same time. So it's clear that they don't commute. So when you make a measure of x1, it definitely perturbs x2. But x1 and x2 are constants of the motion. So all your uncertainty principle trash can collect over here, but doesn't leak through Hamiltonian dynamics back to x1. So that's how back action evasion works in this scheme. So x2 starts fluctuating wildly, but x1 is just perfectly clear and clean without any added noise to it from the measurements. Okay, so that's the dream of a back action evading measurement. How do you do that? Well, you do that with two tones. You have a cavity, a parametric system where you pump on the red and the blue, and you overlap the up conversion with the down conversion, and the field inside there is now being modulated at the mechanical frequency. This is the field that you end up having inside the cavity when you have these two tones. And it has a lot of great features. It turns out that it only couples to one quadrature. Formally, it's a quantum non-demolition measurement of the harmonic oscillator. It turns out it also avoids any classical noise being injected from the amplifier, so that's why it's called back action evading. And in principle, you can go below the SQL on that x1 measurement. So that motivated us to try this. And back in Cornell in 2009, we published a paper where this was our precision of, this is a better axis over here. This is the precision on one quadrature divided by the 0 point level. And then the purple points are the relevant ones. As you come down, you can actually get close to 4 times the 0 point level, and then we hit a parametric instability. We couldn't go any further. Okay. So with it measured a single quadrature, we could actually drive the mechanical system at different phases and actually show that, yeah, we could see the motion or not see the motion depending on where we were driving. But the point is that we actually could get down close to around 4 times the 0 point level. Since then, Junho and through his experiments has gotten down to around 1.5 times the 0 point level, but we still haven't crossed 1 here yet. And there's various instabilities that appear that we're trying to learn how to deal with. So that's kind of the state of the art on back action mating measurements. Okay, so that's kind of the summary of where we're at with small mechanical structures at quantum mechanical limits. It's pretty amazing. You can get down to the ground state now. You can couple the qubits. Andrew's experiments show that you can just ping pong back and forth a single mechanical quanta. A lot of the things that we talked about from more than 10 years ago have just become reality. People can do now. So the field is really interesting. A lot of the when you look at the field as well, you can see that friction is a big part of the story here. So Andrew Cleland's experiment where he was playing, the h bar omega was going back and forth with a qubit. The Q of his mechanical device was less than 1,000. And it really limits the coherence of what he can do with this kind of physics. So dissipation in this kind of piezoelectric material was a real problem here. This is John Toffel's device from Jilla. It cooled down to around 0.3 quanta. But again, it's microwave noise that appears in the cavity that keeps it from cooling down to 10 to the minus 2. Right? Their coupling is much stronger than ours. And boy, if they could follow that curve down, they'd be into really cold states. But they can't because of dissipation effects in the jitter of the circuit. Oscar's device cooled down to around 0.8 quanta, and that was just through brute force. They if the frictional device, the Q was 2 or 3 times lower, they would have not crossed 1, right? Crossed one mechanical quantity. So again, friction played a critical role in making this possible to get slightly below 1. These plots here, I don't know if you remember what they were. Okay, sorry. This is, Shino, do you recognize this? I don't recognize it. 6 millimeter, 12 millimeter, 24. I don't know what this is. Okay, but this I recognize. This is a cutout. This is a plot from Roginski's book where he's showing the Q of sapphire. So the mechanical loss angle of sapphire shows some dissipation peak with sapphire, and then eventually it just comes way down. And here your Qs of in the 10 to the nons. So there's amazing high quality structures that's out there in low dissipation materials, and maybe this will help. Oh, this is silicon. There we go. Yeah, this is silicon versus temperature, and it's showing 10 to the 8, a few 10 to the 9 versus temperature here. So silicon can be amazingly good. Sapphire is known to be amazingly good. Ron should have recognized that plot.
It's from the bottom reference, I guess.
Yeah, exactly. Okay. Okay, so Laura put together this chart here where it shows the quality factor that we find in the literature taken at various temperatures at acoustic frequencies, so like a kilohertz. And so here's OFHC copper, you can get 100,000 out of it in a mechanical Q. Fused silica, you can get 500,000. Regular 6061 aluminum, you get 10 million essentially. Same with beryllium copper. Niobium is 42 million. The special alloy of aluminum is 67 million. We've got a slice of this. We got a piece of the gravitational wave antenna in our lab from the one in Padua. So with some friends there that sent me a 1-inch slab of it. So we have a piece of this stuff. We're going to make a sputter target out of it for making structures. So then here's the good stuff: quartz, silicon, sapphire. Billion, awesome, right? And this is up here at 18. Let's see, the quartz is 18 millikelvin. This is GVAC stuff. And then these are up here at higher temperatures. So it's really attractive to try to play with these things down at millikelvin temperatures and see how they behave. But as I was waiting for my lab to be built here at Caltech, which went on for years and years and years, it was totally annoying. I started when I was riding my bike. I was thinking about what are the ultimate mechanical materials, and I was thinking about sapphire. And but then I used to do superfluid physics. I was like, superfluid, man. I mean, it's really something, right? It has perfect DC motion. So if you have something in perfect DC motion, why can't it have shouldn't it have amazing acoustic motion as well, vibrations kind of. And so, here's some of the properties of superfluid. So the rest of the talk will be all about our ideas with superfluid resonators and where Laura is on this experiment. So superfluid is really squishy. It's got a speed of sound that's 10 times less than normal metals, right? The density is very low. The dielectric constant is 1.05, so it's barely visible. It looks like empty. It's a heavy vacuum, basically, right? It's 1.05, so it's nothing. It's if you make it cold, it's chemically totally pure. There might be frost in there, like snow, but there's no atoms that are dissolved into the fluid, right? The only impurity is isotropic impurity. And just as a point of interest, it's the only material that naturally, spontaneously, isotopically purifies itself as well. Where if you put in helium-3 atoms into helium-4, eventually the helium-3 atoms float on the helium-4. So it's the only matter that's known that actually will separate like that, isotopically. But for our purposes, it's amazing that it's completely chemically pure. It's isotopically very pure. Normal concentrations are 10 to the minus 7. And if you actually go through the effort to try to purify it, you can get below 10 to the minus 14 parts of helium-3 into helium-4. It has this funny transition at 2.17 Kelvin, the lambda point, and below that you start to accumulate a condensate in the fluid. And at zero temperature, the entire fluid is this condensate, with the entire density of the fluid moving with frictionless flow. So there's some macroscopic order parameter, it appears, that behaves kind of like a wave function. There's two places for the entropy in this fluid. It's in these rotons, which have a finite energy for excitation. They exponentially disappear. And then there's the phonons of the fluid, which look like a black body, essentially, like T to the fourth kind of energy density. Superfluid shows persistent mass currents. So if you make a ring, you can have superfluid going around the ring, and you come back tomorrow, it's still going around the ring. It just doesn't decay. The circulation around the ring is also quantized, so the speed at which the fluid goes around the ring only accepts discrete values. So it's like a bicycle wheel that only can spin at these discrete speeds. Okay, so we started to look into this, and we're just asking the question, can a condensate be kind of the ultimate mechanical material? The concept is to put it into a microwave resonator. So to fill this cavity with superfluid, and then the acoustic motion of the superfluid will cause a density change of the fluid, right? The acoustic is just density wave, and that'll modulate the electric field inside this microwave cavity, and that will shift the frequency of the microwave cavity, and it'll become an optomechanical circuit, just like we've been using for our little circuit elements. The frequency of this microwave container will be shifted by the acoustic motion. Okay, so that's the concept to keep in mind. Okay, so here's what we got. This is old data from 1954, which shows the acoustic attenuation length for helium-4 for longitudinal sound versus temperature. Here's a Kelvin, here's 0.1 Kelvin, and then here's some T to the fourth. Okay? And so the attenuation, this T to the fourth was kind of a surprise. And there was a battle in the literature that went on for a couple decades over, whether the Russians and their, 4-phonon process is the right description, or, this T to the fourth can only come from a 3-phonon process. But if you have a 3-phonon process, you have to have the right curvature of the dispersion relationship for this to actually work. Blah, 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 blah. It turns out that everything works out just fine. That a 3-phonon process with a negative number here for gamma, for this term here, everything works and you have a 3-phonon process. So that you get a T to the fourth dependence on the dissipation. The physics of this, like where's the friction coming from? It's that the black body sound, so the fluid has this acoustic sound in it, right? Just a black body, and that's causing density changes of the fluid. And those density changes are causing, through the Grunheisen parameter, speed of sound changes. So the speed of sound is changing due to the fluctuations in the density. This is the parameter here that's causing low frequency acoustic mode to get scattered up into other modes. That's the nonlinear coupling. It's just the stiffness of the fluid getting stiffer as you press on it. Okay, so there's various relationships that people come up with for the theory of this kind of dissipation. And the most compact relationship looks like this. And so there's Grunheisen parameter, there's the density, normal things, and then T to the fourth, and then times the frequency here. So if you take the results from these early experiments and extrapolate them down to 10 millikelvin, and then at lower frequencies at 3 kilohertz, you find out that the attenuation length should be 3 billion meters. And if we can cool down to 1 millikelvin, then it's just 3 10 to the 13 meters. So the intrinsics of the fluid should be, it could be made exceptionally low, is hopefully negligibly low.
The fact that it's G+1, not G, is that significant?
Yeah, I don't know the answer to that, because
Even
then,
without
because if G equals 0, then you still have something. Laura, do you know? That's a good point. Yeah, that's a good point. I don't know the answer. Because you think that there always would be a process, some spontaneous emission part, but I don't. We've discussed it only briefly, I think. That's a good question. Let's make a note. We'll make a note of that. Look into that.
Has no one measured the attenuation below 150 millikelvin?
Not that we could find it.
Okay.
Yeah. I mean, people basically got the story right in 1950 and are like,
Okay.
I guess that's it. What is interesting is that you can move, if you go to high frequency sound, you can actually see the T to the 6th. If you press on the fluid with high pressure, you can change the curvature of the dispersion relationship, and you can make it have some crazy steep. But you'd have to work up in the tens of megahertz or higher. So that is interesting, you can see that. Okay. So the intrinsics of the fluid itself, just through its own nonlinear restoring force, looks like it can be arbitrarily low. I mean, really low, right? Because we know how to make things cold. People cool samples of helium down under a millikelvin. It's possible to do. It's not easy to do, but it's possible to do. So you can make the fluid as frictionless as you like for the intrinsics of that process. There's another mechanism for dissipation, and that comes from the helium-3 impurities. This is where we think it should come from. And it should act as a normal gas inside the can here. And like I said, it's only part, 100 ppb of helium-3 at normal concentrations, and then you can make it lower. But there's two contributions from that make dissipation in this case. It's from the viscosity of the helium-3 atoms, and then also from the thermal properties. So as you make a cycle where you compress the fluid, the particles get hot, and then there's a heat transport mechanism to the cold side, and then that relaxes the pressure difference, so you don't get all the pressure back. So there's a thermal elastic and then a viscosity part. So you can work through all that, and you find out, you get some equations here, and we don't quite know how to deal with it when the mean free path of the particles become big compared to the container, because it's not clear how they're going to scatter off the walls. And the walls can be made smooth, reasonably smooth, and the wavelength of these particles at these low temperatures can be quite long, so they should look really smooth. So it should look really specular. So we're not sure how it's going to work out when you get down to really low concentrations and at low temperatures. Did I say that right, Laura? Is that the correct way to, more or less? Yeah, but the point is not clear. It's not clear. Okay. So this is what we think the Q of the superfluid resonator would be versus temperature for various concentrations of the helium-3 in there. So there's some nominal 10 to the minus 6, say, some impure stuff, and then if we purify to 10 to the minus 9, 10 to the minus 10, 10 to the minus 12. So if you get down to these low temperatures here, it's like 5 or 6 millikelvin, depending on the concentration, you can span from a few billion up to 10 to the 11, something like that. So people purify these kind of levels in their laboratory. So these are not numbers that you can't achieve on your own dilution refrigerator and get helium samples this pure. Okay. So the next dissipation mechanism that we were thinking about is just acoustic loss out of the container, right? So when the superfluid is vibrating, let's say in the right cylinder, then there's the fluid is pushing on the end, say, and that's going to launch some acoustic wave into the copper can. And you can figure out through, Laura's figured out through finite element simulation what the energy stored in the copper compared to the acoustic energy in the helium. Now the copper has a high frequency or a higher frequency vibrational modes, so the copper is essentially in a DC kind of response, right? The superfluid is doing this 3 kilohertz kind of vibration, and the copper can has modes, let's say, of 10 kilohertz or beyond, right? So it's a much stiffer container. And so the acoustic motion is essentially just DC static expansion and contraction of the copper. And so you can just apply a pressure field inside here that's modulated and figure out the distortions of the copper compute the energy stored in the copper, and you come up with this. Then to figure out the friction, then we just use the loss angle on copper, and we know the loss angle on helium, so we can figure out what the limitation would be from this acoustic resonator from this kind of loss of the copper. So what you find out is that the quality factor in a copper container, so these are the data. So copper has a Q of 10 to the 5, we've gone through all this. And then this will limit the Q of this kind of system to 10 to the 8 if we use a copper can. 2 10 to the 10 for beryllium, 10 to the 11 for niobium, and then sapphire 10 to the 13. So the intrinsics of the stretching of the container can also be engineered to be quite low. So that's a good thing. And I think the reason this works is that the helium is much squishier and has lower frequency modes. You're not resonant with any of the modes of the container. Okay, the next thing that Laurie's looked at is the coupling between the superfluid acoustic motion and the frequency shift of the microwave mode, right? In the optomechanics, this is the kind of standard optomechanics thing. You have a mechanical oscillator, electrical oscillator, and then some coupling between them. And this frequency pulling is what is the coupling constant. And so the frequency pulling, given that the dielectric constant of helium is so weak, the frequency pulling for one phonon in the superfluid is 10 to the minus 6. So it's a really tiny amount. In the mechanical structures that Jun Ho works with, this is around 5 or 10 hertz, where one mechanical quanta pulls the cavity by 5 hertz. Okay, so the coupling is weak, but it's not infinitely weak. You still should be able to read this thing out to the SQL and for reasonable pump powers. And I forgot to include that plot, but the point was that with this kind of coupling strength, if we had around 1 volt per meter in this cavity, that would give us the SQL on the superfluid motion. Okay. So it's a really tiny line width. So you don't have to pump very hard to get the amount of noise in that very narrow line is not much. So it's the line width that really makes it possible. But it should, like I said, be about 1 volt per meter inside this can. Okay. So then you can start asking questions now. All right, suppose we do this and we get some really high Q superfluid oscillator. Now, what are we going to do with it? And this is a question that one of the reasons why I hope maybe this community might actually be inspired by this possibility that there might be some interesting experiments to go after. I have a hunch that having a really high Q mechanical oscillator of this size scale that we could read out at the SQL would be an interesting thing to work with. That there'd be fundamental physics that we can attack with it. But here are just some basic ideas. So one thing we looked at, which turned out not to be a good idea, was looking for gravitational waves with this thing. And the point is that you can look for very tiny stretches of this container. The fluid. You can look for if you're reading out the motion of the superfluid down to the SQL, maybe a gravitational wave would come and excite the motion of the fluid. And so I found Blair's old book on gravitational waves, and he presented a model in there of about like a 1 millisecond strain pulse coming from some collapse of something or other, and that would excite some energy density, and that we can push into this oscillator. And so you can work through all this stuff, and you find out that the energy sensitivity that we would have on detection, this is like a Weber bar basically. So you're looking at excitations of something that a harmonic oscillator that would get kicked by this, right? And this term here, which is the amount of thermal noise coming into your detector during the time of this impulse, this because of the Q of our superfluid should be very high. This is just negligible. This is there's no quanta coming in during a 1 millisecond time period. You don't have any. You have 10 to the minus 4 of a quanta. The other part is just the readout of the simple harmonic oscillator, and that's always going to be a quanta. So it doesn't look like a particularly well optimized scheme for detecting gravitational waves, because this is just for your amplifier detection noise, and then your thermal noise here is far below that. You're relevantly below that. But nonetheless, you can figure out what the strain sensitivity be for different size superfluid oscillators. And so for what we're thinking of, where we have, we're thinking of this would be a liter here, right? This is a 1 liter device, and it has pretty horrible strain sensitivity, 10 minus 12. But if you go to a cubic meter of stuff, then now you're talking. You're talking about something that's interesting, 10 minus 21. But now we're back to something humongous, like a big cubic meter, and you might as well be talking about Graham, right? Which is for Sadi's kind of experiment. So, you know, I don't think this is necessarily the way to go, but it's interesting to think about. Okay, so I should have had this slide in a different place, but I wanted to tell you that we're thinking about other designs rather than copper. Another design we're thinking of is a sapphire resonator that has a channel that's been machined into it. So 2 sapphire pieces where it's been cut in half, a channel put in place, and then we fill superfluid into this channel. And this would be a way to have fluid going around the ring with high Q acoustic modes, but have it in a sapphire container which has really high Q microwave Q 10 to the 9 and really good mechanical Q 10 to the 9. So this is a second design that Laura's been working on. And we have those pieces being made now. This is the bottom piece which shows the superfluid channel, and then this is the stub, the little stem on the end that will hold on to it with.
Why is this geometry better than couldn't you just make a cylinder out of this as well?
Yeah, this is nice because it's well known how to make whispering gallery modes around this thing. This will support whispering gallery modes, and I think if you start with a can, then you start to have to figure out how to coat it with some superconductor or some if you want to make a resonator. But just a pure dielectric resonator, you can just go with this whispering gallery mode. That's at least what we're thinking. I don't know if it's going to be better or worse, but the material properties are much better, right? It's a better material system. This is a dummy device that we've had made where we'll measure just all the microwave properties just to learn how to do that. And there's another view of this thing. Okay. Sorry, the slides are a little bit out of order, but anyway, this is the number state lifetime for various Q superconducting superfluid resonators. So a Q of 10 to the 10, 10 to the 11, 10 to the 12 versus the temperature of the bath that you're coupled to. So here's 10 millikelvin. So we should be in number state lifetimes that are just absurdly long, 10 seconds, 100 seconds, 1,000 seconds, which is pretty amazing. You can nearly go out for coffee and come back and one quanta hasn't come into your superfluid resonator. Okay. So this is the slide that I hope that intrigues you about maybe to think about what might be possible. So let's just think about this for a second or two. So let's go back to an arrangement that's a can, a right cylinder, and then inside the cylinder is the superfluid. And I'm going to model the superfluid as just the mass of the superfluid and then some effective spring, whatever determines that spring that gives me the right acoustic resonance, right? So it's essentially the whole mass of the fluid that's moving. So this will be right to a factor 2 here. Okay, so the mass we're talking about is 10 grams. The frequency is 3 kilohertz. The effective spring constant is really stiff, 1 million newtons per meter. The temperature is we can get down to, let's say, 10 millikelvin. Let's just suppose we can get to Q of 10 to the 10. If I have this kind of system here, and if I shake this system up and down, if I take this whole can, I've got this internal mass spring system, and I shake it up and down here. So I shake this boundary up and down. That's the container. The internal mass will move Q times as much. Okay? So I have some high Q oscillator inside this box, and I start to shake the box with resonance. The mass inside moves a lot more when I'm shaking the boundary. So the thermal motion of the helium at 10 millikelvin is around 1/10 of a femtometer. That's the effective motion of this fluid, acoustic motion back and forth. Which means that if I have this fluid in this thermal state here, 1/10 of a femtometer, and I can read it out. Suppose we should be able to read out to the SQ on this, so we should be able to see the thermal motion without any trouble. So if you can read out the thermal motion of this thing to this level, it means that you have sensitivity on the boundary to Q times less than this, which if this is 10 to the 10 means that you can see if the boundary is shaking here back and forth at 10 to the minus 26 meters. So it's really a crazy number. I mean, you just imagine that. I can see whether this thing's shaking back and forth at this kind of absurdly small distance, right? Only at this one frequency. Maybe I could broaden it some through some, pumping it hard and broadening it some, but not by much. So, but anyway, nonetheless, at this one frequency, I can tell you whether the boundary is moving this amount here. This corresponds to a change in the fractional length of this container of 10 to the minus 25, assuming that it's 10 centimeter kind of device. Corresponds to an acceleration sensitivity of 10 to the minus 18 Gs. Okay. You can then also figure out, if I had a gravitational force nearby, like through like a 10-gram object, 30 feet away, oscillating back and forth by a centimeter. That should be enough to excite this mass to this thermal level here. So if you can read this out to this level, I should be able to drive it with small masses, just directly gravitationally. So anyway, it's pretty crazy sensitivities, at least on just the back of the envelope, of what you'd expect for the change in shape of this container or the shaping of this container, either way. So that's what I hope intrigues you. I mean, are there fluctuations in space and time that are this scale? Is there some fundamental physics or fundamental limits we can put on physics by seeing these kinds of small distances?
That's just H there too, isn't it? Delta XC over L.
So this here, this is the strain sensitivity, yeah.
10 to the minus 25.
Yeah.
That's okay.
But if you had a gravitational wave come by and couple so weakly to this thing, that's when you go back to that Blair analysis, the amount of kick that it gets from a strain going by is relatively weak, because the mass turns out to be small. So it doesn't couple well to some perturbation going by that then causes it to stretch back and forth. That seems the problem. It's, people figured this out, I'm sure, 30 years ago. To detect a gravitational wave, you need mass. Okay, that's clear. But this number by itself, if there's other fluctuations that cause the length of something to move, this is the kind of sensitivity we should have. Presumably, if we can actually get an oscillator in that kind of thermal state. So it has to be vibrationally isolated, all that kind of stuff.
Would it take like a year to rig it up?
Yeah. Yeah. But maybe you could, we think we can pump it hard enough that we can broaden the line. So you can pump on the red side hard enough. You don't get more sensitivity in your like force detection and all that, but you do have something that's faster. So our numbers suggest that you should be able to cool it, and this is also as a cooling process. So you should be able to broaden it by, from microhertz up to millihertz, something like that. So still slow. Here's one other intriguing idea that we've been thinking about as well, and also discussions with Marcus Aspelmeyer and folks about foundations of quantum mechanics and connections with gravity, is this whole Penrose mechanism. And this experiment kind of highlights how uncertain it is what this mechanism is even all about, and how you would calculate it. So for instance, the basic mechanism is if I had a superposition of two masses separated by delta x, there's some gravitational energy between these two superpositions, which is already a totally wrong idea, because you don't, in the hydrogen atom, compute the electrostatic interaction with the electron with itself. You only compute the electrostatic interaction with the nucleus, and then solve this wave going around. But anyway, if you take this energy here, and then use time energy uncertainty, this gives you the Penrose decoherence time. And he has problems with the fact that in quantum mechanics, time is a parameter, right? It's just a parameter of the system. But in GR, it's the actual space-time distortion. How can you have a superposition of space-time like this? So it's beyond what I understand. But this is how he suggests computing the fundamental decoherence time for a superposition of a massive particle. Okay. So, but it's totally unclear how to compute this. All right. So, for instance, suppose that you had this was your superfluid oscillator, and it's this is a 10 centimeter kind of thing, and the SQL is like 10 to the minus 18 meters in this case, and you take as the gravitational energy separating the superfluid just by a few SQLs. And so the radius here you would take as the radius of your superfluid, the mass is your superfluid, and you find out that the gravitational energy in that case would be 10 to the minus 45 joules, tiny energy, and the decoherence time from the Penrose mechanism would be 10 to 11 seconds. So you would never have a problem from gravity if you computed it this way. But its mass is not distributed totally uniformly, right? So in a silicon crystal, say, we know that the atoms are just periodically placed. This is perfect. And the mass is concentrated at the nuclei. And so in that case, you can think of the superposition is actually where each nuclei of this massive object is going into a superposition of here and there, and I compute the gravitational attraction or energy between the nuclei in itself, and in that case, if I do it for all the atoms in there and sum them all up, I get a much bigger energy. Okay, so the matter is not uniformly distributed like in this case, but it's actually a bunch of point-like cases where you're at 10 to the minus 15 meters, so the denominator changes a lot, and you get a much bigger energy in a much shorter time. So it's not clear at all what is going on with this Penrose thing, how to compute it. And to be frank, I don't understand how to compute it for a superfluid. I don't even know how to think about the mass distribution. I mean, is the mass of a superfluid of a condensate just a perfectly smooth matter wave, or as opposed to a crystal where it's this point-like distribution of mass? So there's a lot of questions I have about how to compute this. Anywho, that's basically what we got. So Laura has she has her containers. She's got 3 different designs that she's making. She's got a copper can that's just straightforward. We're going to cool that down first. She has similar to the can. She has a lump of niobium. We bought 20 pounds of niobium and making a superconducting resonator out of that. And then we have the sapphire design. The sapphire design, I think, is probably the best design, but it has the most problems with sealing the 2 surfaces together to make it superfluidly tight, and so that's why we have the niobium pieces as well. But we should be able to cool this down over the next months and over the next year, produce some basic data. I think in the end it's going to be how well we can acoustically isolate this thing through its supports. But people know how to do this kind of stuff, right? I mean, the LIGO guys know how to acoustically isolate stuff. Tobar shows Q of 1 billion in a quartz little hockey puck that's heavily clamped on its edges. Somehow he avoids acoustic loss there. So there's clearly ways to avoid the acoustic loss, and I think we just have to learn how to do it. But I think what I hope what might happen is that somebody might be intrigued by these numbers here. By these kinds of numbers, the sensitivity on the shaking of the container or the distortion to the boundary, that there might be some fundamental physics that we could put limits on by just observing this superfluid thing. So anyway, that's what I got.
For the can, I was thinking, I'm predicting that you'll see anomalously low Q because of the roughness of the inside. The fluid seems to me almost like optics inside of a cavity. So it seems like the roughness inside of the can will produce some anomalous scattering between acoustic modes of the helium. And so even if they're all high Q modes, if you try to measure it, you might see this sloshing between acoustic modes of the helium. But that's, given finite element tools, you should be able to figure out what that number is.
Yeah. Well, I mean, in the optics case, the roughness, so you have, if you have a perfectly smooth thing, then there's beautiful interferences that happen that keep the radiation pattern at long distances from having any finite power. And then you put a little perturbation as a roughness, now that is a power that then radiates, it's unbalanced by something else, right?
Yeah.
So in this case, the superfluid, the roughness on the walls, it would just be some extra acoustic radiation into the boundary.
Well, for fine length stuff, but I meant if you have since the mean free path is so long, if you have a curvature or torsion of like some long wavelength thing, that could slosh between low frequency modes of the image. The more of a coherent effect.
Yeah. Yeah.
This thing doesn't seem so hopeless to me. I feel like you should be able to use some coupled resonance kind of trick, even besides pumping. If you had a few of these things, you can use one of them to broaden the other one. And so you wouldn't get 10 to the minus 26 over a broadband, but you could broaden it from
Microhertz up to...
microhertz up to tens of hertz or something, and then it could be useful again.
Yeah, we should talk about that. That'd be interesting to know more about. So coupled oscillator physics, basically.
Yeah.
Yeah, there should be many different modes inside this thing. Some of them have different acoustic radiation out the end, so we'll have to just check it out and see what happens. But does anyone off the top of their head have any is this kind of distance scale? Does anything interesting happen at this kind of distance scale?
Pulses.
What's that?
Pulses, if you can do it at 100 hertz or kilohertz, you can and keep it up for a year. You have a chance to compare with
There we go, there we go. All right, good, thanks. Now we know why we're doing this.
Or is the Earth orbiting the sun?
Technically.
Yeah. Yeah, so we just have to keep it going for a year.
And modulate it,
And modulate it.
cancel out the Earth orbit.
Yeah. Well, anyway, if anyone wants to talk about it, I'll be around, so. Yeah. Good. Thanks.